ahead and get started unless anybody has any questions. Okay, so Kyle's going to go over the demographics real quick and the fall cyst prediction. So go ahead, Kyle. Hopefully you can share your screen.
Is that showing up for everybody now?
No.
No. Of course not. How about now?
Turn on your video.
Yeah.
Which screen does everyone see? Oh, here we go. Too many options. There we go.
Still got nothing.
Still got nothing.
We've got it now.
Check.
All right, looks like it's starting.
Come up for me.
We've got it, John.
Awesome.
Okay. So there we go. Now it works. All right. So I'm going to cover the brine shrimp demographics that have occurred since March. So if we jump into this, and hopefully things will move along. There we are. All right. So lake temperature for this early on this year, we followed pretty well with the average. So on this graph, the red line is going to be the current year, 2020. The black line is the average since 2003. And then all of the other color squiggles show all the different lines, all the years from 2003 to 2019. And so if we follow the red line, it looks like we were a little colder in April, a little warmer in June. And then now sitting here in July and August, we're above the average for the last 17 years or so. Nothing too alarming. You know, you kind of smooth this line out. Looks like we're right in the average for water temperature. Definitely not the hottest August we've seen. We'll see how this last run. We did get one more run in on Monday that we haven't quite finished counting. So we do have some new data that we can go over in December. Looking at the chlorophyll levels for this year, we started out above average. Had a nice little boost there in March with all the runoff and some of the good sunshine days that we had there. We did expect kind of that bigger hatch. We had kind of quite a few cysts left over in this fall or in the spring, looking in January and February, up close around 40 cysts per liter. And we did see that big hatch, which led to this decline in chlorophyll here in April and May. But we did pick up the rebound in May and June that we missed last year. If you guys remember from last year's tag meetings, that we just had that flat line all year. This year we did actually catch the rebound. Moving into salinity for this year, again coming in low for salinity due to all the snowstorms that we got early in the year. January, February, March looked pretty good. April was super dry and everything started to increase in salinity, and we're sitting right on about that 17-year average. Right. Moving on to the cyst densities. So as I stated before, we started in just a little bit higher than average with the cyst densities, and then we've progressed just kind of holding above average throughout the year. Likely due to going through that starvation cycle early. We'll see that there have been some females with cysts as we get moving on here into the next few demographic slides. So Nauplii this year, due to the weather and we had some boat motor failure issues, we didn't make it out very much early in the spring. I think we had 2 runs in January, 2 runs in February, and then only 1 or 2 in March as well. And so that's going to play into the prediction because we just have very few runs early on in the spring due to, like I say, the boat failures, and then also trying to find a safe social distancing protocol to be on the boat together. Limited our availability to get on the lake. So we kind of missed this first peak of Nauplii. And the reason I say that is because by the time we made it out in February, there were 0.2 per liter, so an average of 0.1 for the month. And then in March, we had 0.78 Nauplii per liter. So sometime that hatch occurred somewhere in late February, early March. I don't think we made it out in March until about the 10th. But since then, Nauplii have tracked. They stayed kind of low through May and June, but then have rebounded and definitely got our second generation here in late June, early July. Looking at juveniles, this is how I know that we missed our Nauplii peak, is when you look at the juvenile averages. This is one of the highest juvenile counts we've ever had since 2003, peaking at almost 25 per liter. So those had to come from somewhere. So likely we just missed the Nauplii stage of the first generation with our limited lake runs. Ever since then, juveniles have been a little bit suppressed, likely just because we're missing those peaks with our limited sampling efforts. Moving on to males. Male density has really just tracked that 17-year average right up until the end of May. Then they were suppressed a little bit, but that was when we had our chlorophyll dropping off. So we would expect to see some shrimp loss at that time. And then since then, they have rebounded to nearly right on the average for August now. Females are kind of a similar story where they track maybe just a little bit above average, go through that same starvation cycle, and have still been suppressed here for just non-gravid females. But that is likely due to the fact that when we move on to females with eggs, we're seeing above average levels of females producing eggs currently. Looks like it took a little while longer to get to maturity and actually start reproducing. There again, that could be we just missed some of this first peak, but it's, they're definitely producing now and definitely producing above the average for the last 17 years. Females with cyst density stayed flat through the early summer. And then once they've gone through that starvation cycle, we definitely saw a pickup in cyst production recently through late June, July, and August. And we still expect to see more cyst production coming on in September, October. But this early cyst production is definitely not outside the realm of what we've seen in the past. I mean, we've got 2 or 3 years that show quite early cyst production at the current levels that we're seeing. Total adults kind of follow that same trend as where the males do, where they just track right along with the 17-year average, go through that starvation cycle. We lose some shrimp, but numbers have now rebounded to the point where they are right on about average. So get into the forecast. So as I mentioned before, with our limited runs, this is based on 3 data points. We had 2 runs in January, 1 run in February that doesn't show Nauplii. So it's going to be kind of a rough prediction, but it does show that we were a little bit on the high side at 42 per liter on the low side to 47 per liter on the high side, which translates to a prediction of between 82 and 68. So it's going to fall somewhere in this section of the downward arm, just being that we're going to definitely be on the density dependent side of things going into this year, very similar to what we saw last year. So we should expect somewhere, worst case, we should expect at least 75 cysts per liter. When you remove the outliers from those 3 samples, we back up slightly up the curve into this slightly better area where we're 34 to 42, which then moves our prediction to 115, between 115 and 82 cysts per liter, with an expected average of 98. So right near that 100 cysts per liter mark. And I did just an experiment just to see, because the Nauplii in February were 0.2 per liter. So if we look at maybe including that one, so this is kind of a caveat just to show that, you know, if we include that one more data set that we would normally throw out just due to the rules of how we use the predictive model, the rules that Gary set up for us, is that we, as soon as we see Nauplii hatch, we remove that data. But if you include that data, it does show that we back up even slightly further up this curve and end up in the 28 to 34 region. So what this shows is that every prediction for this year puts us on this density dependent downward curve. But depending upon how things go and how we actually see the resources used throughout the year, we could actually still end up pretty high at nearly 145 per liter. So we would expect to see somewhere in this portion of the curve with our final coming out in the fall. And I think with that, I will take any questions that anyone has. I don't see any in the comment section right now.
Does anybody have any questions about the prediction or the demographics? All righty then. Well, then that'll make things easier.
All right.
So let's shift over to the nutrient work that USGS is doing. Corey or Ryan, I don't know which one of you guys are presenting that, and hopefully you'll be able to do the same thing Kyle did, share your screen and provide your presentation.
Yeah, you bet. So we're going to both be presenting. So I'm going to start, and I'm going to change the screen that I'm presenting here. So John, if you could just let me know when it shows up.
Yeah, I've got my fingers crossed. So
Okay. So let me know when it shows up there, John.
yeah, sometimes these things take a minute, but it
I
looks
see
like
it.
it's loading. You're good.
All right, excellent. I'm going to use you as the guinea pig, John, because yours seems to be about the slowest as to when it shows up and everything. So there you go.
Big surprise with that.
Yeah, exactly. So, all right, well, we'll just get going here. And yeah, we're going to cover kind of the normal stuff that we normally cover on this. I'll cover the monitoring, the stream flow monitoring, the lake stage monitoring, et cetera. And then Ryan will take over on the nutrient side of things and talk about that. So, and I assume, and John, that you can see my laser pointer here.
Yes, I can. Sorry.
Okay,
I
perfect.
muted myself.
All right, perfect. All right, so let's get going here. So the lake stage today. Today we're at 4193.2, okay, which is down about 1.4 feet from our March meeting. If you go back and look at the notes in our March meeting, you will see that I predicted that we would get up to 4196 this year, and we did right there on this day. There was one day, a big wind event got it up to 4196. So I'm going to say that my prediction was good. Really, it wasn't. So I mean, so I made that prediction in March, and then April hit, and we kind of talked about what happened in April, which nothing good happened in April. And really since then, it's been pretty darn dry. So really, we kind of peaked out at about 4194.7-ish is about where we peaked out. And so we're down about a half a foot from a year ago. If you take a look at over the last 3 or 4 years, you can see that obviously the runoff in 2018, 2019 was a big year. So that was about a 3-foot gain in lake elevation in the South Arm that year. This year was kind of, well, disappointing, right? So we ended up with about 1.5 feet of rise this year. So again, it's you know, just we thought it was going to be a good runoff year, and it didn't end up being all that good. If we look at the last 10 years, it just kind of put it in context. The last 6 or so years, we've kind of been hanging out in this range here, this 4192 to 4195 kind of range. Remember, the historic low was 4191.35 back in 1963. So, you know, we haven't gotten down there, but we've been close. In the fall of 2018, we were close, and then we had a good runoff year. So we'll see how things go this year, and hopefully we'll have a good winter this year, and we'll fill the lake up, maybe get another 3-foot rise next year. Who knows? I won't make any predictions on that at this point. My predictions aren't worth all that much anyway, so I wouldn't put too much faith in those. If we look at the last 100 years, you can kind of see we're kind of hanging out at the lower end, just like we were back in the late 50s, early 60s. It was kind of in the low range, but yeah, we're definitely down at the bottom end of lake elevation. If we look at the north arm, again, you know, we're at 4192.8, so it's about 4/10 of a foot of head difference between the two, which is typically what it's been during the reduced inflow time of year. So there isn't a whole lot of inflow coming into the lake right now. During the spring runoff, we'll see that head difference kind of get to like 0.7 feet of head difference, or even greater than that. So right now it's hanging out about 0.4, which is typically what it is. If we look back over the last 3 years, it kind of looks like that, which is similar to the south arm. And if we look back over the last 10 years, obviously the big thing here is when the new breach was opened in December of 2016. So, you know, we had this big declining trend as the culverts were closed. The breach was opened in December 2016, and we shot back up and have kind of been following the south arm ever since, which is what we would expect. The flow monitoring at the new breach. Now, this is not part of the funding that's provided by the ecosystem program, but I think this group is kind of interested in it, so I'll go through and talk about this. So we've been making monthly measurements since December of 2016 to kind of capture the average flow conditions, and this is slated to continue at least through 2021 as part of the monitoring program that's in place associated with the new breach. And then we've had this goal, and we've reached this goal of continuous flow measurement at the new breach, both bidirectional flow, north to south, south to north flow at the new breach with real data display on our webpage. This is what it looks like back in March and April, and the beginning in May. This is the south to north flow portion of it. These red marks here are the monthly discharge measurements that we make. So you can see that we're where we need to be in our continuous flow measurement. Now, if you were to go look at this web page today, what you'll see is you won't see discharge. We've got what we call a rating flag on there, which means that we're working on the rating, which is the relationship between the observed data that we get at the site and how we can turn that into discharge. And we've been having some issues out there lately with some of the equipment, and I'll get into that here in just a second. But if you look at this plot here shows the green line is the south to north flow, and the red line, I'm sorry, I got that backwards. The red line is the south to north flow, the green line is the north to south flow. So back here, the beginning part of May, things are pretty calm and working like you would expect. But we are able to capture these reverse flow events like this one here that are typically due to wind-driven northerly winds kind of driving that north arm water to the south. And we're able to capture that through time. And what's going on right now? So we are still collecting data out there. So once we get the rating figured out, we'll be able to go back and back calculate all this information and populate this data from June until now. But you can kind of see some of these things act almost like a kind of like a step function. So this is the south to north flow, and it goes from 300 to about 500, right? And you see a lot of these kind of steps. And what we think that is caused by is our instrumentation that we have there is that sitting on the bottom uses these bins. Now this is a plot from when we had them out on the lake, and so these cells are really not 0.2 meters thick. They're about a half a meter thick. And so the algorithm that Mike Freeman has kind of come up with to get to discharge at this site looks at the velocity in these cells and finds where it goes from positive to negative, and then picks out that cell as the interface. So let's say cell 4 was showing north to south flow, cell 6 is showing south to north flow, then it's going to say, okay, well, cell 5 is where the interface is. And where you pick out that interface, that goes into computing the cross-sectional area for, let's say, just the north to south region. Well, if you're cell 5 at one instance, and then the next instant you're at cell 6, that's a 1.5 foot jump in cross-sectional area. And so that equates to, you know, there at that location about, I think it's about 200 square feet. So that could equate for, if you've got one foot of velocity, that's about 200 CFS. So what we're trying to do is we're working with the USGS Office of Geophysics, or branch of geophysics, and they have a postdoc there that's interested in helping us. And what we're looking at doing is installing a kind of a conductivity string that has sensors at a very, well, at a more fine interval than what we've got with our ADCP, or with our acoustic instrument. And so we would install this string of instruments through the water column, and then we would be able to use that to pick out where that interface is between the south to north and north to south flow. And that's really going to help improve our computation of discharge at the site. The other thing that we're looking at doing, and that we've actually done right now, is installing a surface velocity radar at the site. So sometimes some of the cells in the upper, in the south to north flow, the data might get a little wonky there, just because, particularly if the interface is really strong, just because you get reflection and refraction of the acoustic waves off of that density difference between the two brines. So we've installed a surface velocity radar that does exactly what you would think it would do. It measures the velocity of the surface flow. So we're hoping that we'll be able to use that as a surrogate for a mean velocity in the upper brine when we're having some of those limitations due to the acoustic instrument and flowing through the acoustic waves going through the water column. So it's still, again, I've mentioned this several times. This is not an easy thing that we're trying to do here, and so we're continuing to refine. What the information that we're providing is obviously much better than what we've had before, where we just had monthly discharge measurements, but we're looking at getting this even better. So we continue to work on that. The inflow monitoring that is funded by the ecosystem program is the continuous discharge gauge here at Goggin Drain, and then the monthly discharge measurements at Bear River Bay. So things are going fine at the Goggin Drain. That site always produces good data. Bear River Bay, we continue to make discharge measurements there as needed. So far this year, these are the discharge measurements that we've made. It's not flowing right now. It hasn't really flowed since June. So you can see here are the discharges over here on the far right side. So during the winter time is when most of the flow gets into there. We had about 370 CFS at the end of June, and it's been no flow since then. We do have a camera out at the site that we check, and when we see flow start to come back up, we'll get back out there and get another discharge measurement, so that we can capture when the flow begins to flow at the site.
Is that a live camera?
It is a live camera. It's actually a game camera. So I guess I mean, you kind of log on and you can connect to it. It's got a cellular modem on it. You log on, you connect to it, and you can have it take a picture for you right then, and you can take a look at that. So yeah, it's a good solution. We're using more and more of those at our gauging locations. And that's what I have. So I'm getting ready to turn it over to Ryan. Oh wait, no, I'm sorry. I've got one more thing here. And again, this is another piece of data collection that we were doing out of Gog and Drain. This was actually part of a Hot Topics grant, and I think we talked about this at the March tag meeting. But just being able to compute the salinity load to the lake from the major inflow sites. So, we've got this same information for the Bear River and the Weber and the other rivers that flow into the lake. So, again, this was a Hot Topics grant. So we are not collecting this data right now, but we were able to go back, and the whole purpose of this Hot Topics grant was to refine the salinity loads to Great Salt Lake. And so here at the Gog and Drain site, we installed a continuous temperature and conductance monitor, and computed a regression between the observed conductance values and salinity, and used the USGS NRTWQ webpage, which stands for the National Real-Time Water Quality webpage. Our regression equations haven't been approved yet. They're going through the review process. So this web page is not publicly available at this time. But as soon as we get those things approved, you would be able to go into this web page and see this. And then if we are able to get funding in the future to reinstall these probes and operate those probes, we'd be able to show real-time salinity loads to Great Salt Lake. But as you can see, as you might expect, the vast majority of the flows come during the spring runoff, and the vast majority of the load for this is the black line here is the load. The blue line is a computed discharge. But you can see for a lot of times during the spring runoff, we're getting 1,000 to 1,500 tons per day of salt, basically, just from Gog and Drain. And so, yeah, we've got this for the other sites as well. And like I said, once we get the regressions equations approved, this information will be available to everyone. All right, that is the last slide that I had. So I'm going to stop presenting, and I'm going to turn it over to Ryan. But while we're doing that, and while Ryan's getting his stuff going, does anybody have any questions on what I've presented?
The only thing, since you did mention salinity on that last thing, I would, since we got a short break, and Jeff, you can jump in if you want, but we have that Salinity Advisory Council that a lot of us are involved in. And I guess probably the only gap in that Salinity Advisory Committee Council, I can't remember, is probably Gary. And maybe if we could occasionally send some information Gary's way, just for him to look at that Salinity Advisory Council findings and where we're going with that, it might be good. And Jeff, did you want to bring anything up with respect to that? Because I think if we are able to have Gary look at some of those, it would at least make me a little more comfortable as far as getting all the lake knowledge involved there.
Right. No, I definitely would like to look really into this, and probably some other. I think that the task that we're working on right now is to identify key salinity ranges and thresholds for the different uses of the lake. And obviously, the ecosystem is a critical component of the lake health. And so we're trying to, for different components of the food web, identify where the ideal salinity ranges are, if there are any key thresholds that might be markers for potentially harmful impacts to those components. And so we're working on a literature review right now, and I certainly can hope to follow up with several of you to make sure we've got the best available information in this. But the objective is to give the state, give the lake users a kind of a heads-up tool dashboard to kind of see, if we see changes in salinity in the different parts of the lake, what does that mean? I think, John, you're on mute.
Oh, yeah. So I did get some of what you said, but we'll have, if we're not presenting or something, we'll have to mute. But yeah, and maybe if we could just send some of that information to Gary, then he'll have a chance to look at it, and then maybe talk about it during the December tag.
Yep. Sounds
No
great.
problem.
Thank you.
Happy to do it.
All right, Ryan.
Well, hello. Hopefully you all see my presentation screen.
Looks good.
Nice. That's a big hurdle for me. I have a webinar disability, but we won't get into that right now much more. Anyway, it's a pleasure to be here, guys. I'll pick up then with inflow nutrient monitoring that is funded through the ecosystems program. We monitor nutrients at 6 inflow sites. These are sampled approximately every 6 weeks. This program began in 2011, and we're collecting samples and analyzing them for nutrients and major ions. And we've looked at this long-term data set in previous tag meetings. It's available on INWIS for you. It's a world-class data set, obviously critical to understanding nutrient mass balance in Great Salt Lake. And this is the data set, for example, that Dave Nass works with to help compute nutrient mass balance in Great Salt Lake, in the water body itself. So that work is ongoing, continues as planned. Let's see, why did that slide not advance? Great question. Okay, now the slide advanced, hopefully. So we're also engaged with the ecosystems program in open water nutrient monitoring in Gilbert Bay itself. And this is sampling that John Luft and his folks conduct every month. There are 4 sites that they monitor. They're shown on the map there. They collect samples from 2 depths, a shallow and then a deep sample. And again, these samples are measured for the same things that the river inflow samples are monitored for. So the nutrients and density, which we convert to a salinity using the Nass equation of state. And just to give you an example of what this open water nutrient data looks like, here I've got the plot on top is total phosphorus. So this is an unfiltered water sample. The units are milligrams per liter. We have a data set like we've mentioned going back to 2011. The blue circles are deep water samples. This is 3510. The light blue circles are shallow water samples, and then where there's shading, we know there was a deep brine layer present. And so if you look at the blue circles, the deep samples, when there's a deep brine layer present, the concentration of total phosphorus, and even if you go to the plot below, which is total nitrogen, the concentrations of those nutrient elements are elevated when there's a deep brine layer present. And then when there's not a deep brine layer present, the values are dramatically less in shallow water. This is just to kind of give you an update on the nutrient values in the lake. Beautiful. One other thing to point out is that right now the deep water samples for nutrient values, both phosphorus and nitrogen, they're elevated and they're looking similar, getting the similar values that we saw before the disappearance of the deep brine layer due to closure of the culverts. So that's just kind of an update on the status of the nutrients in the open water of Great Salt Lake. The next slide, we have kind of the density values monitored out in the open water of Great Salt Lake. Here we have density in grams per cubic centimeter, and as you know, we relate density to salinity through the NAFS equation of state. Here I'm just showing density. We have data for GSL 2565, and which is up in the northeastern part of Gilbert Bay, or actually we would call it Carrington Bay. And then we have data for site 3510, which is basically the center of the south arm. The bottom line is the density values, as we look at more recent data, are elevated in the deep water samples, which are the solid blue circle and the solid green circles. And these density values are looking similar to what they were prior to disappearance of the deep brine layer due to closure of the culverts. So that's kind of the status of the density / salinity in the south arm of Great Salt Lake right now. Okay, that brings us to a very large effort that we're engaged in right now. And this is a study that's being, the principal investigator here is Christine Rumsey. And then there's a bunch of us who are working closely with Christine to make this happen. And this is an effort to quantify nutrient mass and internal cycling in Great Salt Lake. It's an effort to identify the important processes that are moving nutrients from the various pools in the lake. And right now, we don't have a lot of information on that. And the hope is that we can identify areas where these processes are really important, so different areas in the lake where they're important, and then also kind of quantify the rates at which these the nutrient cycling happens. So as it moves from one pool to the other. And the hope is to refine this to the point where it's the kind of thing that can be included in models of Great Salt Lake, potentially a model such as Gary's model that helps us understand, kind of the biological activity out in the lake. So right now, there's not enough information to do that kind of thing in terms of nutrient dynamics. So that's our hope, is that we're able to identify the important processes that are happening in the lake and identify where they're happening. And so, just kind of building on this idea, what processes control nutrient availability? How much mass is recycled back into the water column versus lost to sedimentation, sorption or volatilization to the atmosphere? And this figure on the right is one that Christine Rumsey has shown this group before, and that's a snapshot of the whole idea of this study. So I really encourage folks to, if you have a copy of this figure, if you don't, reach out to us. If you have this figure in hand, you basically know what we're trying to do out on the lake. And it's all about quantifying the amount of nutrients in the different pools, including sediment, pore water in the sediment, measuring the amount of nitrogen gas that's evolving off the surface of Great Salt Lake, looking at nutrient loads coming in from the atmosphere. Obviously, the ongoing monitoring at the inflow sites are giving us information on nutrient loads coming in from the surface water sites. But now we're also, in addition, looking at nutrient concentrations in ceston, in brine shrimp. We have sediment traps on the lake, trying to figure out sedimentation rates and then quantifying nutrients in this sediment that's falling out of the water column. So this is a massive effort to kind of identify these different areas where nutrients are coming and going for the different pools in the lake. And the objective is that we have to quantify the mass of nutrients in those various pools, and then we need to estimate flux rates between the pools using tools such as fixed equations. And then we want to also estimate nutrient burial rates. So we have a kind of an idea of what's being locked away in Great Salt Lake sediments and is no longer available to the biological system there. So it's a big effort, and the field work for this is ongoing right now. So we're in the middle of the effort. The field work started about a month ago, but planning and preparation for this has actually been going on for a year. And so right now, Christine and other crew members are out at a site on the south end of the lake, not too far from the marina, and they're collecting lake sediments. They're collecting sediment samples and extracting pore water. They're collecting ceston, brine shrimp information, and then, as we have mentioned, we have river inflow information. She's collecting samples, water samples at finer depth scales than we do typically, which typically there's a shallow sample and a deep sample. She's collecting several additional samples through the water column. So we have upper brine layer and deep brine layer nutrient information at better resolution than we've had in the past. There are sediment traps out there that she's that are active. They're actively collecting samples now, and then we have the dust traps collecting information on nutrients raining out from the atmosphere. And this is just kind of an example of some of the field work that's going on. So these are photos of the dust traps. There are 9 dust traps. I forgot to point them out on the site location map. It was early in the presentation, but there's 9 dust traps around Great Salt Lake. The photo on the left shows the one that's deployed at Great Salt Lake Marina. You might recognize the beacon, the light beacon there, and that's our dust trap to the left of that. And then the photo to the right is probably Antelope Island. You see Great Salt Lake off in the distance. These dust traps we fabricated here. That metal frame that's holding the funnels, and the funnels have bottles at the bottom of them. We fabricated the frames. The funnel design and the bottle design are modeled after work at Utah State University. So this was a big effort just to get these dust traps constructed and deployed. So they're out there now. And we're looking forward to the results, some of the data from those. Additional field work. So here's just an example of collecting shallow. These are folks collecting shallow sediment off of a sediment sample collected with a box core. This is obviously some very dark and juicy sediment here. And those of you who work on Great Salt Lake would know that when you see sediment like that, there's a wonderful odor that comes off of it. So here's just an example of getting a shallow, like 0 to 2 centimeter depth sample from a sediment sample collected in a box core. So this sample will go off, off to our laboratories for analysis. To the right, this is a photo of some fine scale sampling we're doing in the water column. And we're actually very excited about this. This is a SNAP sampler chain. So those little white containers are actually sample bottles. They're suspended between a concrete anchor, and you can see that anchor in the photo just below the water surface. It's the black object. And then there's a buoy above the top container that keeps those bottles vertical in the water column. So Christine lowered these bottles down into the water column when they were open, let them sit overnight, let everything equilibrate, and then the next day she came back and she triggered and closed the sample bottles. And then here's the photo of them pulling those bottles up. And you can see how there's a color change going from top to bottom. The top bottles are relatively white. This is upper brine water. And as you get to about the third bottle from the top, you can see a slight color change, kind of brown, and that's getting into the deep brine layer. And then the 2 bottles below that are even darker colors. So these are very high quality, fine vertical scale resolution samples of the water column that have since been sent off to the lab, and we're waiting for results on those. This kind of sampling on the right is very important for using calculations to compute flux of nutrients from the deep brine layer to the upper brine layer. That gradient, that concentration gradient, is very important for those kinds of calculations. And this method is going to get us to where we need to be to make those calculations. You guys may recall in previous tag meetings, I mentioned that we wanted to just do some tests of our field methods for this big effort that's happening now. And we did do some testing of our field methods way back in November of 2019. And this is just an example of some nutrient data we collected at GSL 3510 back in November 2019 as part of this test. So on the upper left is the nitrogen mass that we measured in the various pools shown in the pie chart. We have sediment from 0 to 2 centimeters, kind of in the unfilled, unshaded area of the pie chart. The shaded area is sediment from 4 to 7 centimeters. Excuse me, it's the nitrogen mass in sediment in the 4 to 7 centimeter range, and then the nutrients mass in the sediment slurry, pore water, upper brine layer, and deep brine layer water. Those nutrient masses relative to the shallow sediment and the deeper sediment are very tiny. So, you know, the take-home picture with nutrient in sediment versus nutrients in sediment relative to nutrients in water or slurry is that there's an enormous nutrient reserve in the shallow and the deep sediment. And so understanding movement of sediment, or movement of nutrients from the sediment to the water column is obviously very important and is a big objective of this effort. So you have nutrient mass on the left. If you move to the right side of the slide, there's phosphorus mass. It's essentially the same story. The pie charts at the bottom of the page are nutrient mass in water column pools and phosphorus mass in water column pools. We know about the upper brine layer and the deep brine layer nutrient masses. This is work that Dave Naps has done over the years and continues to do. But we have new information now with sediment slurry and pore water that are included, that we can include in the nutrient mass balance picture. So that just is some test data really from November 2019. So we're going to build on that with this effort going on right now. And then finally, I'll just wrap up. In November of 2019, we did very detailed water quality profiles with the YSI EXO2. They were done at 20. The profile step interval was 20 centimeters, so very fine vertical resolution. And we have a total algae sensor on that YSI EXO2 that measures chlorophyll A. And here's just an example from GSL 2767 at 0.51 and 1.4 meters depth. The next column over is chlorophyll A. This is a value reported by the sonde in micrograms per liter. This is just using the internal algorithm built into the sonde. It takes the raw signal from that sensor, converts it to a concentration. And then if you look in the last column, chlorophyll A measured by our lab, you just kind of compare the values. There's really good comparison there. And I'm actually pretty hopeful that with the effort going on right now, where we're doing the same thing, detailed profiles with the sonde, and then also measuring chlorophyll A in our lab, I'm hopeful we can develop some tight relationships between the sonde values and the lab measured values. And then that gets us into the realm where we can do continuous chlorophyll measurements out on the lake using an instrument, which would represent a pretty significant leap in our ability to monitor out there. And then below that is just an example of some 34 to 32 sulfur ratios in the sulfate anion in water out on the lake. We have data for sites 2767 and 3510. You can see a little bit of variability in those values in the middle column. Basically, the more positive the number, the del 34 to S to 32S ratio, the more positive it is, potentially the more sulfate reduction. The more positive that number, that could indicate there's more sulfate reduction going on, which gets to mercury methylization, etc. But the hope is that if we can find a signal in the deep brine layer where we have consistently heavier or more positive isotope ratios, this could be an additional tracer to evaluate mixing and diffusive flux. So anyway, I haven't seen any sulfur isotope data for Great Salt Lake. This is some of the first that I've seen. I just thought I'd show you. And, that wraps up what I have for an update. Bottom line is the field work is happening now for this effort. All right, are there any questions?
So I see that Anne did have a question in the chat box. You want to respond to that about how the differences between the wetting and the drying of the shoreline?
Yes, absolutely. Okay, so Anne is asking, yeah, how do we know how nutrients fluctuate in the wetting and drying of the shoreline? And the answer is we don't know here at the USGS. So that's a really good question. I mean, that would obviously take some almost like a continuous monitoring effort with like buoys along the near the shorelines to kind of get at that. So I don't have an answer for that. We don't know.
Okay, so and the other thing that I wanted you guys to discuss is, based on the contract and the information that we sent out before, is how does this play into Gary's model? How does and is it, could you give us the details on the future work that you're going to be doing and how that's going to populate the model, since this is, I mean, those things are independently, it doesn't help us. We really need to work towards a specific goal with this information. Obviously, nutrients are the huge gap in our knowledge of the lake, and I just want to make sure that we identify the correct things going forward, that we're paying for the right things. And Ryan, would you mind muting your just because there's some feedback there, but so would you guys mind kind of talking through what information you're going to be collecting that will feed into that model specifically, and then I'd like the tag group to respond to that and make sure that we're going in the right direction and we're collecting the right things, that Gary's getting the information that he needs as far as the nutrient inputs to the model. That way, if there's some things that we can cut out or focus on that's a little bit different than what we are right now, that we don't get off on a tangent and start looking at things that we really don't, that isn't going to help us. Would you guys be able, or Corey or Ryan?
Yeah, no, I can jump in on that. So the first thing is that Gary's model right now, it doesn't really have a way to deal with nutrient dynamics, the real dynamic nature of nutrient fluxes in the lake, and that's because we just don't have enough information on that. And that's kind of the idea with this phase 1 approach, which is we've selected 10 sites out in the south arm of the lake, and we're measuring just about everything we can concerning nutrients. And so what we want to do is then use this data to identify important areas of flux, of nutrient mass exchange between the various pools. So with the spatial distribution, we want to identify where those diffusive flux events or processes are happening, where they're happening at rates enough to be very significant that we capture with this event. So the idea is we'll be able to zero in on areas where there's a lot of nutrient mass exchange happening. And then future monitoring will kind of zero in on those areas and those processes, those diffusive flux processes, and get enough information on that to where it could be considered to be incorporated into a model like Gary's. If it never reaches a point where it can be incorporated into Gary's model, I think everybody can agree in this group that understanding nutrient cycling in the lake itself is extraordinarily important. Like, we need to understand what mass of nutrients end up getting locked away in sediment and end up deeper in the sediment, so that it's not available for bio. So that's a mass of nutrients pulled out of the water body and isolated from the water body where it's no longer available for biological activity. We need to understand what mass of nutrients, nitrogen, for example, are volatilized to the atmosphere and lost from the system. We need to understand the mass of nutrients that are actually coming into Great Salt Lake from the atmosphere, hence the dust traps. So this whole nutrient process is one that needs to be understood. I mean, if you have a reduction in the inflows and therefore the loads of nutrients coming in from the inflows, what's going to happen over time? And so we have to know what mass of nutrients end up in sediment and are locked away, what mass of nutrients end up volatilized, etc. So that basic understanding of the nutrient cycle has to happen, regardless of whether or not we end up with a process that can be locked directly into Gary's model. But the hope is we can find some significant processes that should be incorporated into his model. So that's my short answer to, kind of long answer to your question. So this is just phase one. This is just identify nutrient masses in the lake and try to identify where these nutrient exchanges between the different pools are significant. Phase two is to dial in on those significant areas. And
right, and that'll be for the next year, basically. And again, if you, what I would hope is during our spring tag that information, we could get input from the rest of the tag group so that we are focusing on the right things. Like I said, this is one of the aspects of the program that I have probably a weakness as far as knowledge and understanding. So I just want to make sure that the entire group is on board with understanding where we're going and that it is agreed upon that we are moving in the right direction, collecting the right things, not just getting information that isn't gonna benefit us. Obviously, like you said, there is a lot of we've got to understand what's going on with nutrients out there, and that hasn't happened in the past. So this is a huge undertaking, and it's kind of a difficult question to answer. So Gary or Thomas, do you have any I guess feedback for the guys at USGS as far as since you guys are a lot more knowledgeable about this portion of the program, do you see any gaps or things that we should be looking at?
Before those guys respond, I just want to chime in and say, once this field work is done, which we hope to wrap up by the middle of next month, there's a pause in the monitoring, okay, in the sample collection for this, so that we can sit down and analyze this data and produce a publication and share the results with you, with the group, the tag group. And then as a group, we'll decide how to move forward on understanding nutrient cycling in the lake.
John, this is Thomas. I'm happy to make a few comments. I think Ryan pretty much laid it out for us that what we're trying to do here is gain more knowledge of some of the areas that that we're not really aware of what's happening. And you know, we're talking about atmospheric deposition, we're talking about volatilization, loss to the atmosphere, and we're also trying to get some more information about what's going on in terms of cycling of nutrients through the biota, from the DBL to the UBL, or even into the sediments. I think it was interesting to see that some of that information from Ryan is already showing how important the nutrient loads are in the sediments. It's something that we weren't aware of at the, you know, before this work was done. I think what Ryan said really well is that this is a first approach. And it's ultimately really probably just a snapshot. And as these results start coming in, we can take a closer look at it and then try and identify those areas that we think we need to focus on, those areas that are the most important. With regard to process, I think, John, that you did a good job of involving all the TAG members early on, and we were all able to comment on this proposal, and the USGS answered to our concerns and our comments. And so there was a back and forth, and I think that was a good process, and I would suggest that we go through a similar process again once the results of this sort of first sampling effort and snapshot, if you want, have come in. I would like to commend the USGS so far for what they're doing, because it is a huge effort. It's really going to be difficult to gather all of that information. And I think as a first effort, it's good. I mean, yes, we're probably going to have some questions we will still need answers for, and we're going to have to look over time how these fluxes and this cycling evolves. But I think as a first effort, I would commend it as, you know, a good effort. And you, John, as having involved all of us early on in the process, given us an opportunity to comment and try and help guide that effort. And I would suggest we follow that same process going forward. Those are my comments.
This
Thanks,
is Gary. I agree with completely with what Thomas pointed out in terms of both the looking at what's going on in the lake and in terms of the process that went through in working with USGS and putting this together. I think the one thing, and Thomas brought this up, that we need to stress is that this is simply a snapshot view. It's the lake at this year, this condition. And when we go to modeling, we need to know what happens in the lake under different conditions so we can model it and test it. And the problem with the snapshot type view is if we ran this same study intensively, and I don't know if USGS wants to run the same study this, you know, for 10 years into the future, there is no guarantee after 10 years that the lake is going to change enough between years to give us an insight into parameter changes that we would want to put into the model to look at how nutrients are going to be dynamic in the long term or with different weather conditions, etc. And let me just point out, I'll be talking more about this at the end of my presentation.
All right.
Can I just add a few things in here, John?
Yeah, Corey.
All right, thanks, Thomas and Gary. And yeah, just so that everybody's aware of this first one, you know, as Ryan kind of pointed out, we've got like 10 locations out on the lake. This is a very intensive learning experience is really what this is. And so, you know, as we move into future proposals or future sampling efforts, we're hoping that we'll be able to use the information from this to refine where it is that we really need to be out there sampling. And so that we don't have to go out to 10 sites. Maybe we only have to go to 3 or 2 or 5 or something like that. But, you know, we'll let the data tell us that. And as Gary said, and Thomas said, you know, this really is just a snapshot under these lake conditions right now, where the lake is pretty well grazed out right now. You know, so I would think it would be important for us to see what it looks like in the winter when the brine shrimp are all in cysts. And so, you know, again, yeah, this is just a first shot. And back to the process that we went through in developing this proposal, yeah, I think it worked really well with the back and forth with the other members of the TAG to ensure that that the objectives that everybody needs were being addressed. So there you go.
Sounds great, and I agree with my self-admitted lack of expertise in this realm for sure. We'll continue doing the same thing or approach it the same way. So at each TAG meeting, we'll just update where you guys are at with this, and then as we get through the analysis portion and subsequent publication, we'll move on to reviewing your findings and then try to develop a path moving forward, just as you guys have mentioned, and that way we can at least stay focused on the right things or adjust if we need to. So any other questions for Corey or Ryan? Okay, well, Gary, I'll let you jump into your presentation. And while I got a quick second, I will say hello to Mark Lehman. I have not seen you for a long time, and I just wanted to I'm happy to see you out there. So hello. Glad you're able to join us for this one. Virtually is probably better for you, I would guess. You're on mute though. Maybe you don't have audio on your computer. I just wanted to acknowledge your existence there. So I'm glad to see you.
Can people see this?
I can't yet.
Anybody be able to see it?
I can't yet.
Okay, why won't it show? Okay. Will you allow? Try again. Says it won't share it. Must grant permission. Somebody know how this works? I know how to do it in Zoom, but it's not working here.
Yeah, that's what I was afraid of. Brian, do you probably have a little better understanding of this?
I tried this yesterday, John, and I just had to click the present now button in order to be able to share my screen. So I don't think I'm going to have a lot.
That's what I'm doing. And I hit present now and it says your entire screen or a window.
Oh, you have to select the application. So if you click up in that window and select your desktop, and then the button should turn blue and you should be actually able to share.
Hey, Gary, the way I did it is I just selected a window and then it gives you all your windows there and you just choose the one that you want to show.
Okay, I went down below and I've got my PowerPoint there. And then it gives me above my browser with Google in it. And then I hit present now. And it says a window. And it says must grant permission in order to save, present.
So who's hosting? Is John Luft's account?
Yeah. Who's hosting? You have to give me permission.
It should be me or Jessica. I didn't want to get bogged down with stuff, so I'm not sure, but it doesn't give me
An option.
See, that's the problem. Unless I have permission to display, it won't let me.
Sometimes it depends on how you joined the meeting and if you were part of the group or if you clicked on it. Different links take you into different groups and some have permission and some don't. I don't understand it, but it sorts. So you've been put in the no box, Gary.
Thanks.
So I don't know if there's anybody that could explain it to any of us.
Is there a way to send your presentation to someone who has already presented that we know has authority?
Yeah, maybe send it to Kyle and then he can just go through it and you can talk.
Okay, I'll try that.
And while we're waiting, maybe Mike, would you mind, and we'll just, while Gary's doing that, I'll just let you go ahead and
Are you out already?
Discuss what you wanted to about the nutrients. It's a good time anyway to do that.
Will do.
Kyle, excuse me, if Kyle could send me an email so I can attach it.
Okay, go ahead, Kyle. Mike, you want to go ahead then?
There now. I'm ready to go ahead. You want me to?
Yep. Shoot for it.
Well, I wanted to talk about the role of birds in nutrient cycling in the Great Salt Lake, especially with nitrogen. I'm going to group the birds by how they could contribute to the cycling of nitrogen, what their input is, and talk about them. The first group I want to talk about are white-faced ibis, or those birds that that roost or nest in the marshes around the Great Salt Lake. They go out into the uplands, especially agricultural fields, feed on insects, come back, defecate in the marshes, and so they are a great contributor to the nutrients within the water systems of the Great Salt Lake. You can see the main areas here, the swamp symbols where these guys are located. There's about 200,000 of them. They're big birds, so they're a pretty good importer of nitrogen. But on the first cut, they may not be that important to tag because they are upstream of where USGS has where they're sampling nitrogen. And so you're picking up whatever contributions they're making when you sample the nitrogen in the water columns. They're important. Certainly we need to figure out what would happen if these populations collapsed. But on the first cut, they may not be that important. Another group of these birds are American pelicans. Again, huge birds. There's 10,000 of them. but they do the same thing. Almost all of their foraging is done outside the Great Salt Lake, the Great Salt Lake itself. They come back, they have a colony in the North Arm right about where the G of Gunnison Bay is. And so they're contributing a lot of nitrogen to Gunnison Bay, the North Arm. But it then becomes a question of, well, how much of the nitrogen that they are contributing to the North Arm actually winds up in the South Arm? And that's probably a relatively small amount. So on the first cut, they may not be that important. The third group are gulls. They also are big birds, a couple 100,000 of them. They stay here year round. Their colonies are scattered throughout the South Arm. They forage both inside the lake during the nesting season, and the winter almost entirely outside it. They're bringing back a lot of nitrogen, introducing it into the South Arm, and that's something we don't have a handle on. That is an open question. We also have a number of birds, grebes, phalaropes, avocets, and stilts. Now, they probably have no effect on bringing nitrogen in or removing it through their foraging because they're feeding entirely on stuff in the Great Salt Lake. In essence, what happens is they eat brine shrimp or brine flies. They come from the Great Salt Lake. The birds ingest the stuff, they defecate it out. And so by their feeding, they're probably not having too much impact on bringing nitrogen in or taking it out from the Great Salt Lake. One question asked by this group earlier, well, it's a question, you've got 3 million eared grebes, let's say. That's a lot of, they each weigh about 400 grams, half a kilometer. And so their body mass as a group is probably over 1 million kilograms. And so that's a lot of body mass leaving the Great Salt Lake in November and December. But they're also bringing about that much in when they come here in August and September. So that may be pretty much a wash. The one difference is we don't know what their mass is when they're arriving on the Great Salt Lake, how much of it is protein. We don't know how much of their body mass is muscle. We're hoping to go out next week, in fact, with the Great Salt Lake Ecosystem Project to sample some of these birds. But unless there's a change in mass or body composition, they're probably not having much. It's probably over the year net neutral in that they're coming in and they're leaving. But I suspect they're heavier when they leave the Great Salt Lake than when they arrive. And I suspect they have more muscle mass when they leave than when they arrive, because they have much further to go once they leave the Great Salt Lake than they did moving from their summer grounds to the Great Salt Lake. If we look at another thing, I said that they come in, they leave, and so that's net neutral. But one thing they're doing while they're here is going through a complete molt. And I have calculated what that's going to bring in terms of nitrogen. 3 million grebes. Can you all hear me? I'm assuming. Anyway, we have 3 million grebes, about 0.4 kilogram body mass. So again, you've got 1.2 million kilograms of eared grebes. Feathers make up 7% of the body mass of eared grebes and other birds. So that means you have 84,000 kilograms of feathers that are being molted into the Great Salt Lake. Those 84,000 kilograms of feather, almost all of it is protein, 82%. And so you wind up with 68,000 kilograms of protein. 16% of protein is nitrogen. So you're going to wind up with about 11,000 kilograms of nitrogen being introduced into the lake by the feathers of eared grebes. They're by far the biggest, one of the biggest birds out there in terms of molting feathers. They're very numerous. So if you add in things like the phalaropes, pelicans, stilts, maybe it's twice as much as just eared grebes, but probably even less than that. So, and I also want to point out that these feathers do not float on the water. They float in it. They're like an iceberg. A tiny bit of it is above the water line. And so most feathers probably aren't blown onto the beaches or away from the Great Salt Lake. They're in the water. There's another number of organisms that can digest feathers, and so the feathers, the nitrogen in the feathers is probably being released into the upper water column. I want to compare that. This is from Dave Knapp's paper on dissolved nitrogen loads in kilograms. We've said that it's about 1.10 to the fourth from feathers. Dave is looking at 1 to the 6th for dissolved nitrogen coming in from the lakes. And so we're contributing, the feathers from eared grebes contribute about 1% compared to what the rivers are bringing in. We also wanted to look at what impact the birds have on the distribution of nitrogen within the water column. And I'm assuming here that there's a deep brine layer, so we're going to look at that. While they're live, brine shrimp use osmoregulation to maintain basically neutral buoyancy in the upper water column. Their bodies are slightly heavier than the water, so they would sink, but they use osmoregulation to be neutral. However, dead brine shrimp don't osmoregulate, and so dead brine shrimp sink. Once they sink to the top of the upper brine layer. They sit on the top of that upper brine layer for 6 hours to 24 hours. While they're sitting there, they're losing water, they're taking in salt. And so after about a day, they're heavy enough that they sink through the deep brine layer and they wind up on the bottom beneath the brine layer. Once they're there, they don't rise. Birds and mammals, as they're decomposing, rise to the water surface, but invertebrates, brine shrimp do not, they stay there. So what happens if birds eat the shrimp? Where does that nitrogen go? Well, birds produce uric acid. It is a white powder, or in the case of fecal material from the birds, it's a white paste. It also sinks. It sinks to the bottom, same place the dead brine shrimp go. It sinks beneath the deep brine layer. And so you wind up, regardless of whether a bird eats a shrimp or whether the shrimp dies a natural death, they're going to wind up on the bottom below the deep brine layer. So it's not really clear if birds are really speeding up the nitrogen cycle or really changing where these nutrients would wind up. Is that it? Okay, so looking at this then, we're in an interesting situation. We need to find out ultimately what impact these white-faced ibis have, because they are bringing nutrients into the water and probably an important source of nitrogen, but it's being picked up. And we're pretty good except for gulls. And so I think in the future what we ought to do, which was the recommendation of this group in the past, was to study these gulls in more detail in the future, both because about half of the world's population of California gulls nest on the Great Salt Lake, and also because they're probably a contributor of nitrogen into the Great Salt Lake that is not being picked up by these sensors that USGS has scattered around. So thank you.
Does anybody have any questions for Mike? I do have a couple of, I would think that, or at least I always see streaks of brine shrimp, dead brine shrimp on the surface of the lake. So I don't know when it gets to the point where they sink, but.
Well, if you look at shrimp, if you put them in a column of water, a small percent of them float to the surface and are on the surface. A small percentage, about 10% and 10% are in the water column, but most of them tend to sink. And it'd be interesting to actually go out, look at these streaks, because I've seen those things too, and a lot of birds take advantage of those streaks, but to see what actually proportion of the shrimp are in those streaks versus how many are missing, which would mean they're probably in the water column or have sunk.
Yeah, that was some good calculations that you put together for the grebes and feathers and the amount of nitrogen that's contributed by that. That was, I'm glad we have that data from all the past research that you've done. All right, anybody else got any questions?
Yeah, John, this is Thomas. Hey, I have a question for Mike. Mike, you indicated that there may be a difference in weight of the grebes as they arrive on the Great Salt Lake versus when they leave the Great Salt Lake. Do you have any indication on what that weight difference could be?
I have a lot better information on that in a week or two when we analyze the grebes we're going to sample next week, but I would guess they 10–20% lighter coming in than going out. Maybe 20% more muscle mass, that'd be my guess.
Because in that case, would it be fair to assume that if they're 20% lighter coming in, you know, while they're here, those nutrients are primarily cycling, but when they leave, they take those additional nutrients away, and the difference between those would be, rather than what they're contributing, would be what they're actually, it would be a net negative loss.
Right, I would suspect, you know, it's not the entire mass of the birds that is being lost, but it would be the difference. It'd be the difference in muscle mass. It'd be the difference in their body weights between when they come and when they leave. I'm also assuming that the number of grebes flying into the Great Salt Lake are probably very similar to the number that are leaving. I don't think there's much mortality of grebes once they're on the Great Salt Lake. So they would, the birds that die here, you know, they're not exporting it, but I don't think very many die here.
Yeah, it's interesting you bring that up, Mike. I mean, we definitely do have occasional events of big die-offs of grebes. So I have no clue how much that represents, you know, as a percentage of what arrives here, but it would be interesting to take a look at that.
Yes, that would. And some years when we do have big die-offs, you know, that would change things. It also changes things when we have a big die-off ducks that are upstream, but sometimes we have huge die-offs of ducks, and they're decomposing in the marshes, and they are contributing nitrogen to the water column.
Yeah.
Yeah, there is some significant cholera outbreaks on the lake that take quite a few grebes in the thousands, but it's not every year. And Anne brings up a good point. Basically, every species of bird that comes into the lake, their purpose is to refuel for another leg of their journey. So they may be taking more out, which goes to Thomas's point, than what they're coming in with. So there's probably maybe a net loss there.
Yes, I'm sure there's probably some.
And maybe from the sort of initial data that Mike is giving us and his guesswork on how much lighter these grebes are when they arrive, you would still be looking at a same order of magnitude, maybe maximum a few percentage points.
Yeah.
Right, Mike? Either loss or gain, or who knows?
Right, a few percentage points, maybe 10%.
All right, well, we're getting a little behind. Let's try to get...
John, maybe I wasn't making myself clear, but Mike mentioned that the total contribution from the feathers and the molting process would represent maybe 1% of the total nitrogen inflow. If you look at Mike's numbers, you could deduct that even if they take nutrients away from the lake, you would still be in that same order of magnitude, a few percentages of nitrogen they take away from what the inflow is.
Right.
The riverine inflow, I mean. So.
Yep.
Right.
I mean, really interesting numbers, Mike. Thanks.
Thank you.
All right, well, let's try to get to Gary's presentation. Hopefully Kyle was able to get that pulled up.
My fingers are crossed.
Okay, well, we'll hope that works out. Kyle, you want to load that up and share your screen? I'm sure I'll be the last to know.
Hooray. Okay, well, first, apologize for the technical difficulties, and I'm going to have to apologize that I won't have a pointer to be able to point to things on this, and I'll have to tell Kyle, move 2 slides now. First of all, I'd just like to fill you in on what the phytoplankton data looks like so far this year. And on the left is the 1994, when the project started, through 2019 phytoplankton counts by month, and green is chlorophytes. The brown color is bacillariophytes. Blue is cyanophytes, and the fuchsia at the top is various other types of organisms that appear in the phytoplankton. And if you go to the right in 2020, you can see that we're in a period, as we have been in the last few years, of the phytoplankton being totally dominated by the chlorophytes, Dinelliella in particular. So we've entered into a period that fits the long-term, what people thought the lake looked like, dominated by Dinelliella. Those counts go through May. We're doing June, July, and August now. We didn't get June and July done for this meeting because my lab was shut down until the middle of June thanks to COVID restrictions on campus. So we weren't able to get totally caught up with everything, but my technicians are working on it right now, and we will be, I think they've already moved into July counts as of this week. If you go down to the lower left, It shows the chlorophyll values over by month, red being the 1994 through 2019. Blue is this year so far, and you can see a dramatic decline in April-May period of the chlorophyll, and I'm going to talk about that in a little bit later, because this fits in with what Kyle said, that we were on the density dependent side, and that dramatic decline in chlorophyll reflects large numbers of brine shrimp feeding and eating the phytoplankton in the water column. If you go to the right, on the lower right, it shows the maximum chlorophyll that we got in the spring before the brine shrimp hatched out, and it was about on average with what we've seen over the last 10, 15 years. Next slide. And here's how since the start of the project in '94 to present, you can see that the chlorophytes in the upper left have been increasing since the project started. Bacillariophytes phytes have gone through a couple of blooms, but now are at very low numbers. Those are the diatoms. And then the lower left, we have the cyanophytes, and they've gone through a couple blooms during the period of our study, and they're now at relatively low levels, and cyanophytes are the blue-greens. And then we have the other groups that we get in the phytoplankton, and you can see in the last, say, 2 years ago, and going back about 4 or 5 years from then, we had a little blip, and that was when we started to see euglena in our samples, and they had previously been at very low levels, and again are virtually zero levels for the last 2 years. I'm going to come back and talk about the blooms of the cyanophytes and the bacillariophytes a little bit later. Next slide. This bit is a repetition of what Kyle largely presented. It just points out the blue line is what's happening so far this year. The red line is the red line is the historical data that we've got since 1994. And you can see already we have higher densities of cysts in the lake, and that's due to the shrimp already going through a period of starvation, of low food availability. You can see that the nauplii, and Kyle pointed out that may be due to reduced sampling this spring, that the nauplii this year were at lower numbers than had been previously seen. However, if you go to the lower left, you can see that the juveniles really spiked this year, spiked much higher than any previous measures that we have in the lake. And those spikes in juveniles had to come from somewhere, as Kyle pointed out. And that's probably due to a low count in terms of the nauplii due to lower sampling this year, given restrictions with the virus. If we go to the adults on the lower right of the slide, we can see here that it's matching up pretty closely to what the long-term average is for the adults, a little bit lower, but not tremendously a tremendous amount. What this points out to us is those juveniles did not survive to become adults. Must have been a large die-off in the juveniles. Next slide. So what I did to point out what has gone on in the lake is I converted all the counts to adult equivalent numbers. So in other words, this is converting nauplii to body mass, how many nauplii you would have to have the same body mass as an adult, how many juveniles you'd have to have the equivalent body mass of an adult. And so this is adult equivalents per liter. And you can see that there was a huge increase observed this year early on in the adult equivalents compared to the red line, which is the historical value. This fits again with what Kyle pointed out, that we are on the density dependent side of the curve for cyst production. And if you go then down to the lower left, you can see there that there's usually a spike in the adult equivalents, the red line, historically, and then that's equivalent, or occurs at when that occurs, we get a decline in the phytoplankton because they've grazed it down, the phytoplankton, they fed on it. You can see on the lower right that this year that response was much more severe than it has been in previous years. That spike of adult equivalents that we've never seen before has really dramatically decreased the abundance of phytoplankton in the lake as measured by chlorophyll A. Next slide. Okay, let's talk about the model. So the model is basically composed of 5 modules. The first module on the left is the abiotics influences. That's your salinity. That is your nutrients. That's your temperature. I'm going to talk about that at the end today relative to nutrients. The next module, and the arrows point out the feedback from each of the modules into another module. The next module is the phytoplankton in the lake. The next module after that is the shrimp population. The next module is the bird population, or the grebe population in particular. And the last module that you see there is the output of data. That is the measurements or the predictions that come out of the model after it's flowed through all 4 of the previous modules. Next slide. Okay, so in March, our March meeting, when we were face-to-face, I presented how the data in the model was improved and the modifications that we had made from previous versions of the model. And those modifications all dealt with shrimp demography and the actual structure of the model. So the changes in shrimp demography included some accounting modifications, keeping track of the demography of the shrimp population. It included putting in the commercial harvesting of the shrimp population. It included overwinter survival measures that were dependent on water temperature and the maternal food intake. It included hatching temperatures, being temperature dependent. Previous to that, there was just a constant for hatching. Now it's built in as temperature dependent. And the model was made in terms of structure to be able to run for multiple years rather than 1 year at a time. And we set the limit in the new model up to 5 years at a time, with each year being able to be changed for environmental inputs. Those are the abiotic factors. So you can run it for 1 year, it pauses after 1 year, you can change the environment. A wet year, you can change the amount of nutrients, etc., coming in, and then it'll run for the next year. It'll stop and then let you modify the environmental inputs again. Next. And so all of those modifications were on the module dealing with the brine shrimp. And that's what this slide presents. And I won't go into detail. This I've already pointed out what they were, but each of those circles represents new additional data that we put in, we're able to add, that modified the brine shrimp module. Next slide. And then this shows how the flow of the model goes. Each of these sliders that are there, you can modify the value of the inputs to them. You can then run the model. It gives you an output. It then goes back and gives you the slider so you can change salinity, nutrients, etc. It'll run it then for another year, and it'll do this for 5 consecutive years at a time. So we basically now have a model that will make projections 5 years into the future, where you can change and say, we had a drought year, the next year is a high water year, what's going to happen? You can make those sorts of predictions. Next slide. So what I wanted to point out is what we've done since the March meeting, and that's improved the data for the model. And we focused over since March on the phytoplankton side, a module in the model, which was modifications to phytoplankton production, the biomass of phytoplankton, and the rate at which that phytoplankton can grow, and the grazing by the shrimp of the different types of phytoplankton. Next slide. Okay, first thing, we now have a complete array of responses, environmental responses by the phytoplankton. We have it for Donnelliella, that's the green line here. Their responses to different salinities, different temperatures, and different nitrogen levels. We have a common, perhaps the most common diatom or bacillariophyte in the lake, Nitzschia. That's represented, their responses there are represented for salinity, temperature, and nitrogen. And then we have one of the most common cyanophytes, blue-greens, which is Coccicloris, and their response to salinity, that's the blue line there, that's their response to salinity, temperature, and to nitrogen. And you can see that what's interesting here is that the blue line and the brown line, the blue line being the cyanophytes, the brown line being the diatoms or bacillariophytes, they are responding very similarly. They are responding, they do the best, they reach the highest abundance at low salinities and drop as salinity increases. On the other hand, Donnelliella, the chlorophyte, the green algae, respond best, they grow the best at the higher salinities. If you look at temperature, you see that Donnelliella does best at cool water temperatures, but the diatoms and the blue-green algae do best at higher water temperatures. All three respond very similarly to nitrogen in the water. So we have two groups of the phytoplankton that do well at high temperatures and low salinity, and Donnelliella does best at high salinity and low temperatures. So we now have very detailed information on the responses of the three most common forms of phytoplankton in the lake that we can include in the model. And these types of data came from laboratory experiments where we tested all of the responses under different temperature, salinity, and nutrient combinations in environmental chambers in little mesocosms that we were studying. Next. Okay, that was the maximum abundance achieved. This is the growth rates at which they approach that maximum abundance. And you can see that, again, the growth rate for it responds somewhat differently than getting to the maximum abundance. The cyanophytes, the blue line there, their growth rate goes down dramatically as salinity goes up. Their growth rate goes up with temperature, and of course their growth rate goes up dramatically with nitrogen. On the other hand, the diatoms, the brown line, and the green Donnelliella there, the green algae, they're not as affected by salinity, and they're not as strongly affected in their growth rate by temperature, and they're not as strongly affected by the nitrogen. It is the cyanophytes, the blue-green algae, that are most variable in terms of their growth rate with the environmental conditions. So now we have the maximum abundance each of the phytoplankton can achieve, and we have the growth rate at which they approach that maximum abundance. Next slide. Okay, so this led us to ask the question that we have all been talking about for years in our group. What created those diatom blooms, the bacillariophyte blooms that we've seen in past years? We now know the response of one of the most common of those diatoms during those blooms to different environmental conditions. And did those environmental conditions serve to be favorable to the diatoms? Well, salinity, there's no effect of salinity in the lake on the diatom blooms. Next. If we look at temperature, there is no significant effect of temperature on the diatom blooms. Next. There is no effect of nitrogen in the lake on the diatom blooms. So none of the factors that we have measured that affect the growth of the diatoms, it can explain those blooms we saw in the lake. However, wind speed seems to be correlated with when we get diatom blooms. If you plot wind speed versus the percentage of diatoms that we get in the phytoplankton in the lake annually, the average value for the year, there is a strong correlation and significant correlation there. And the wind speeds are for the Salt Lake City Airport. The reason why, I know Jim's going to ask this question, why didn't you use Hatton Gunnison Islands? Well, the Salt Lake Airport has a longer term data set that matches up with these measurements, and you can count on the data being there every hour for every day of the year. Whereas Hatton Gunnison Islands are down, failing to record data a lot of the time. We also know that Hatton Gunnison Islands on the lake measure wind speeds that are about 20% on average greater than Salt Lake Airport. So we can modify that. You may say, if you look at the wind speed there, you've only got a difference of wind speed of basically 3 to roughly 4 meters per second. And you say, that's not very much. Well, the actual force of the wind in terms of creating turbulence in a lake is the wind speed squared. So even though that's not a big amount, the difference in wind speed, when you calculate it on force, it becomes much greater. Adding all of these things, wind speed, salinity, temperature, and nitrogen in a multiple regression, there is no significant effect except for wind. So none of those other environmental factors seem to be important. Next, click. Okay, this actually improves, this wind relationship improves if you use only the wind speed in the wintertime. It jumps from an R value of 0.71 to an R value of 0.85. And if you look at the blooms that we see in cyanophytes, they occur about, on average, 2 years after an increase in the diatom bloom. So somehow those diatoms and the cyanophytes are related to each other within the lake. Why would there be a relationship between those two sets of phytoplankton that are lagged by 2 years? And why would wind perhaps explain the diatom blooms? Well, it turns out Nitzschia and the Coccicloris, the 2 species that we've measured, are also major parts of the microbialites in the lake. And I'd like to suggest that the wind is breaking off the microbialites and suspending the diatoms and then eventually the cyanophytes in the water column, and that may explain those past blooms that we saw that had been were extremely rare and unexpected in the early years of our study on the lake. So anyway, that's where this data gets us in terms of explaining what we may have seen in the past. Next slide. Unless somebody has a question on this at this point. No, okay. We also now have on those same species of phytoplankton, the rate at which the brine shrimp will feed on them. And as expected, the feeding on the Donnelliella, the green algae, for each of the stages of the brine shrimp is greater on the Donnelliella, a little less on the Coccicloris, which is the blue-green algae or cyanophyte, and the lowest on the diatom, the Nitsia, that we have tested now, these common forms of phytoplankton in the lake. So that's typical. It's what we had expected to see, but now we have actual intake levels that can be built into the model. Next slide. Might point out that the nauplii do not feed not at all on the diatoms. And that's probably because the diatoms are too big for them to ingest. We can break this down, these feeding rates, to the effects of salinity on each brine shrimp stage of development, temperature effects, and the abundance of the food, how that affects the rate that they're being fed on. And so we now have a complete array of being able to say, under a particular environmental condition, what is the rate that our adults, juveniles, and nauplii can ingest foods. Again, this is done with little mesocosms in the laboratory in environmental chambers. Next slide. So anyway, here's the phytoplankton module. Lots of arrows, lots of boxes, and interactions going on. The circle of the black up there reflects what we now can put in terms of the abundance of each of the three categories of phytoplankton. The blue circle there brings into effect the differences in which those phytoplankton taxa can grow. And that's particularly important as they're grazed down by the brine shrimp and they have to recover after being eaten. And so this tells you how fast the food, each of those three categories, will be recovering. The brown down below, the brown circle, deals with the brine shrimp grazing, differentially grazing on each of those taxa at different temperatures, salinities, and abundances. And the big red circle deals with the accounting and the flow changes that we had to make in that module to bring in all of this detail. Next slide. Okay, so here's the model again. On the right, we have the environmental conditions, the abiotic. Next module is phytoplankton, which is what I just spoke to you about and we modified. The next is the shrimp module, which we modified and got up to completed in the, presented that in the March meeting. Then we get the birds eating on the shrimp, and then we get the output to the model. The big weakness in the model right now, as Corey and everyone else pointed out, is that now abiotic module. That abiotic module for nutrients is the problem. The way nutrients are handled at present in that module is there's assumed to be a constant amount of nitrogen available, and each year with the flow of water coming into the lake, it is diluted. Its concentration changes, and that then feeds back onto the phytoplankton production. That is our biggest weakness there. There is no particular way of at present of being able to deal with the details of the nitrogen and possibly phosphorus dynamics. It's been suggested that under certain salinity regimes, it might be that phosphorus could become limiting rather than nitrogen. And we would need to know how the phosphorus and nitrogen numbers are changing in the lake under different conditions. Next slide. So this is what an example, as I pointed out, of the growth rate of the three types of phytoplankton. What the model needs to be able to project, to forecast changes of conditions in the future, what the model needs is a graph like the graphs like this. And instead of the rate of growth, which in this case is for phytoplankton, which is chlorophyll per liter, we would need to know nitrogen and phosphorus abundance per liter under different salinity conditions, temperature conditions, and amount of sources of nitrogen that could be decomposed. So we might want to know if there's lots of brine shrimp dying, few brine shrimp dying, lots of phytoplankton in the water, few phytoplankton in the water. That would be the equivalent of different levels of nitrogen for microbes that are decomposing. So what's important with what USGS is proposing to do is it tells us where some of this decomposition is taking place and is important for the phytoplankton in the lake. So it tells us in what part of the water column this could be important, but it doesn't tell us how the rates of these things will change under different environmental conditions. The problem there is, even if, as I pointed out already, if you studied it for 10 years, you might get 10 years that don't differ at all in terms, or not differ much in terms of water temperature or salinity, and you wouldn't be able to generate these types of relationships to build into a model of the lake to be able to forecast what happens if you throw in more nitrogen coming from a stream. What happens if you have more shrimp that are dying off and you have a different salinity? There's a lot more dynamics underlying this than just the spatial arrangement of where this might take place in the lake. So what we need is the microbial activity in the lake below the brine, in the deep brine layer, in the water in the deep brine layer, in the sediments. We need to have the microbial activity above the deep brine layer, in the water column, and in the sediments, giving us rates of nitrogen and phosphorus release that we have an equivalent number like this that can be built into the model, so we can project conditions that we may not have seen in the past, but may eventually occur in the future for managing the lake. Next slide. And that is it. Questions?
Krishna had a question in the chat box, and I don't know if anybody else had anything, although I think a lot of that you've answered in the past. I mean, this is a model, it's not perfect, but...
Yeah, well, first of all, the question of, there are unknowns and variabilities. First of all, the variability, by how we can point out the unknowns. The model is built with basic certain assumptions, and you're locked into those assumptions by the model. So that's where you're stuck. And what you can test then is compare the model to actual responses that you see in the lake under different circumstances. If the model fails, then you've got to reevaluate your assumptions. The data that's going into the model. Pardon?
Go ahead. I'll ask my question.
Okay, the variability in the model. Let me point out, there's much lower variability in the model than what you're expecting based on in-lake observations, because all of the numbers that are going into the model we have generated from laboratory experiments under controlled conditions. So that variability is reduced to a much lower level than what you'd expect if you were building a model using field observations. The field observations are what you're going to test the model against. So anyway, that's where we're at right now. And when we deal with uncertainties, once the model's up and running, we can look at sensitivity of the model to different parameter values and see how confident we are with those predictions as well. So, I mean, there's a way we can do, the plan would be once the model is up and totally running, we would do sensitivity analysis. Does that answer the question? Okay.
Yeah.
Hey, Gary.
Yeah.
Go ahead, Thomas.
Yeah, Gary, this is Thomas. I'm not sure I followed entirely, so I understand what you said with
You're
regard
breaking
to
up. You're breaking up. I'm having a hard time hearing you.
Sorry, is this better?
Yeah.
So I'm not sure I understood entirely. So you're saying that the peak in bacillariophytes and cyanophytes as a result of an increased wind speed. You were mentioning that there was a lag of about 2 years when the cyanophytes would peak as compared to the bacillariophytes, but you're relating it all to the microbialites. So I'm not quite sure I understand where that lag would come from. If the wind speed, so maybe you can elaborate on that. Maybe you have some ideas as to why.
You know, this is a hypothesis at this point. One of the things that's going on is I think that the bacillariophytes, the diatoms, provide we know from reading the literature on the microbialite that the diatoms provide a structure, a rigidity to the biofilm. And if they've broken away for some reason, maybe then other portions of the biofilm further on later are more susceptible to be broken away.
Okay.
The point comes down to this: neither the bacillariophyte or the cyanophytes, when they're blooming, are not under favorable growth conditions for either of them. And that's what we thought we would see, would be that there would be more favorable conditions. And in fact, some of these blooms are occurring under totally unfavorable conditions for the cyanophytes and the bacillariophytes. Now, let me throw out another hypothesis here. Now, don't hold me to this. I'm just hypothesizing here. What happens if the conditions, because these are the things also making up the microbialite, if the growth conditions are not good at a particular point in time, are we also reflecting not only wind, but I don't want to say a die-off, but certainly a less healthy biofilm on the microbialite, which could make them more susceptible to being broken off with the wind.
Okay.
All of this has been, the analysis now, I've broken it down month by month on salinity, temperature, nitrogen, and wind on a month-by-month basis. And wind is the only thing on the diatoms that comes out. And the months that come out that are important are November, December, January. Those 4 months are the wind speeds, and those months are the most important. And that's average wind speed that I'm working with. I even tried the analysis on a monthly basis on the average of the maximum gust for a given day. So I took the maximum gust on a day and averaged that, and that didn't work as well as looking at the sustained average wind speed in those winter months.
Yeah, it's interesting. I mean, without the information on the microbialites, you would be really lost as to find a causation, with regard to that correlation with wind speed. So I can see where your hypothesis comes from. Obviously, you'd have to, figure out if that's a true causation, but.
Well, other studies that have been done with diatoms have looked at nutrients and found a relationship with wind, like in the Baltic Sea. And in those studies, they found that with the higher wind speed, they got upwelling of nutrients, but there's no relationship between the wind speed and nutrients in the Great Salt Lake.
Yeah. That's interesting. I had another question, Gary. Early on in your presentation, you identified maybe a shift in the phytoplankton structure towards a higher percentage of chlorophytes.
Yeah.
Do you expect any effect of that on the oviparous reproduction?
Well, they do. They reproduce better on the chlorophytes, both with the both forms of reproduction increase with the chlorophyte.
Yeah. So that could result in a higher cyst production, is what you're saying?
It could. They do tend to produce more live young with the chlorophytes than with then it's harder for them to go switch from one to the from live young to the cysts when the diet's chlorophyte. They have to starve more. But this year they really decimated the phytoplankton.
Yeah. Yeah, and to that effect, I just want to make a comment that we also had this pretty high peak of juveniles, around 20, and we were lucky that we were actually able to capture the nuclei peak. And the peak that we had was 70 nuclei per liter, just above 70, which
that would make sense, yeah.
I think so.
So, I mean, Kyle's comment that we're on the density dependent, that downward slope of the cyst production function is definitely seems to be what's going on in the lake.
Yeah, definitely. I would agree with that. Yeah.
All right.
Any questions and comments I had, John?
Very good. Anybody else real quick? I know there's a couple of questions in the chat box, but in the interest of time, if there's no others, we'll try to finish up with Brian's presentation.
I was going to ask Gary a question really quick. It's more of a back to his hypothesis on increase in diatoms, windstorms. Is it feasible that these windstorms are kicking in more silica input into the lake from the dust? Or do you think they're getting knocked loose from bioharms?
That could be the case. I didn't present silica for the diatoms. We actually varied silica in the water as well, but it had no effect on the other two, so there was no, I didn't present it. It affects the diatoms, but it is much less of an effect than nitrogen fertilization. So I can't think that that much silica would be added that it would have an effect.
Okay.
Unfortunately, if we go back to the USGS data on, or actually, yeah, not even USGS, past studies prior to USGS work on the lake, we have very few measures of silica in the water.
Okay. And then kind of back to the chlorophyte temperature relation.
Yeah.
Obviously things are getting warmer around here.
Yeah.
And your graph showed a slight increase from 20 to 30 degrees. They'd actually do better in that. I don't know if that's just by chance.
That's not significant. If
Okay.
you do the statistics on it, testing between 20 and 30, that's not a significant change. It's a flat line essentially.
Yeah. Let's pay attention to the phytoplankton we collected recently, because there really isn't a portion on the lake that's actually green right now. It's all brown. Let's see what shows up in the phytoplankton.
Yeah, those counts are being done right now, Jim.
I mean, like a week ago. You haven't got those yet.
Okay, we haven't gotten those yet.
Let's see what's in those.
Okay.
I don't think they're doing well because of the temperature, is what I'm saying.
They may not, yep. And if you think about it, if the greens had been grazed down, If
Yeah.
the greens are established, right, they're going to maintain themselves. But once they're grazed down to a low level by the shrimp, their growth rate does not allow them to recover if the temperature is high.
Correct. I would agree.
So that's what could be happening. They got grazed down so much that the lake, they haven't been able to recover.
Yeah, they're getting hit from temperature and shrimp.
Exactly.
Okay, well, let's try to finish up real quick and let Brian give his presentation about some of the data that we've collaborated on with Audubon to, and I realize all of you know that we've done that 5-year waterbird survey 20 years ago, but since then we've collected a lot of bird data, and Brian was kind enough to put the effort into getting that assimilated, and so I'll let him go through a quick presentation on that.
Can you hear me okay, John?
Yes, we can.
Okay, sounds good. I'll start sharing my screen now. Let me know when you can see the PowerPoint.
You are good to go.
Okay. So this is the first time I'm speaking to the group, so I'm happy to have the chance to share this body of work with you. My name is Brian Taverny. I'm the Saline Lakes ecologist with National Audubon. I've been with the Saline Lakes program in National Audubon for about a year and a half now, a little bit more than that. But this is some work that I've been doing with Tim Meehan, who's also with National Audubon, in conjunction with John Neal and John Luft with GSLEP, to look at a really unique data set that they have, a long-term count data set for shorebirds, waterfowl, and other waterbirds at Great Salt Lake. And I do want to emphasize this is a unique data set. This type of, the length, the period of time over which this data has been collected is rare when you look across the saline lakes in the arid west. And by doing a trends analysis on this data set, obviously that plays into, or has the potential to play into some decisions around what species to prioritize for conservation and management. That being said, though, there are always caveats when interpreting these types of trends analysis that need to be kept in mind when you're working on those prioritization decisions. And I'll talk about that a little bit more later on. Let's see if I can get this to advance. There we go. So John referenced this earlier, but I did want to take some time here just to emphasize that we're building on a foundation that was laid when GSLEP was founded back in 1996. And they recognized that there was initial information need that they had to really understand what bird species were using Great Salt Lake, when, where, and in what numbers. And so they undertook this massive effort over a 5-year period from 1997 through 2001, surveyed birds in 53 survey units scattered across the lake, up to 17 times a year, stretching from spring migration all the way through fall migration. And at the end of that 5-year period, they produced a summary report. You can see the cover page of the report there on the left-hand side. The full body of the report is located at the link down below. And in essence, they were able to address those questions that they had, the descriptive questions about what species, when, where, and at what numbers. And I've got just a snippet of the results you can find in that report on the right-hand side here for the American white pelican. On the left-hand side of this particular snippet, you'll see that there's a plot of species counts against calendar dates, giving you some sense of when this species is most abundant at the lake. And then on the right-hand side, you've got an accompanying map, which shows the survey units and the average abundance for the American white pelicans during this 5-year survey effort. So giving you a spatial perspective on when they might be, or where they might be most abundant at the lake. So as that 5-year survey effort was wrapping up and they addressed those basic descriptive questions that they had, GSLEP decided that they wanted to continue monitoring at a subset of units fewer times a year to really allow them to get a sense of how numbers might be changing across time. So they decided to focus in on a subset of units that were highly used and presumably of high habitat quality for the birds that they observed during this initial 5-year survey effort. And that's where Audubon comes in. We entered into a data sharing agreement with GSLEP probably about 2 years ago now, just before I joined the program, to help them standardize this long-term data set that they have, and then to do a trends analysis using the data set. And so this is just a basic overview of the data that we were working with and the analyses that we conducted. As I mentioned, they scaled things down from the original 53 to 24 survey units pictured on the left-hand side. And as a reminder, these are units that they observed a lot of, the birds were really abundant in these units, and the assumption is that these are high habitat quality areas for the birds. Temporally, the data that we were working with stretched from 1997 through 2017. And over that full 21-year period, they consistently were doing surveys in 2 periods in spring and 3 periods during the fall. And so we were able to look at seasonal count trends for species and groups. And the species and groups that we looked at, there were 30 individual species, 7 groups. The reason we had to use some grouping was there were just some species that observers had a really hard time identifying or differentiating between. So you can think about a quick example being Western and Clark's grebe. So that's a group those are 2 species we looped together, sorry, not looped, but lumped together into a single group. And so using this data set, we conducted trends analyses, and I'm going to be describing to you 2 different types of trends we derived from that analysis. One was an aggregate trend in which we summed counts for a species or group across all 24 survey units and asked, how is that summed count changing across the 21-year period? So that's what we mean by aggregate. We're aggregating across all 24 survey units that you see pictured there. And then there's also a local set of trends analysis that I'm going to be describing to you. And this is where we looked at what's going on within individual survey units for species and groups. We fit our models using mixed effects models. We had some parameters to control for the fact that you had nested observations within survey units and within years. And we used a Bayesian approach to come up with our model parameter estimates. So just jumping quickly into some results here, these are the aggregate trends. So just as a reminder, that's where we summed counts across all 24 survey units. And this table is a simple summary indicating the number of species that were increasing, stable, decreasing in spring and fall. And so a quick take-home message here is that over that 21-year period, we observed that there were no species or groups that were declining in either spring or fall. At least there was no statistically significant declines observed. The other quick take-home message here is that when you're looking at those species and groups that were increasing, there were a greater number of those that were increasing in spring than in fall. A bit more quantitative information here. When you're talking about those species that are increasing, the numeric value associated with that increase ranged anywhere from 3.8 to 13.5% year over year. So that's the rate at which the species and groups were increasing. To make things a little less abstract, this is a list of those species and groups that we saw increasing in both spring and fall. And I'm not going to go through these 2 lists exhaustively, but I will point out that those species and groups marked with asterisks have been identified as species of conservation and management concern by regional, state, and local planning documents. And they include the widgeon, the cinnamon teal, eared grebe, great blue heron, long-billed dowitcher, and curlew, mallard, and white-faced ibis. And then you've got the eared grebe showing up again in the fall. So the aggregate trends are suggesting that counts for species are stable or increasing, at least in those 24 survey units where GSLEP has continued to do counts. What do the local trends suggest? And so again, the local trends are referring to what we observed in individual survey units. And here, what I'm showing you is a set of 4 maps that summarizes for each survey unit rather, the number of species or groups that showed increasing or decreasing trends. The increasing trends are illustrated in the top 2 panels, the decreasing trends in the lower 2 panels. The left-hand side shows the results for fall, and the right-hand side show the results for spring. And so not to spend an inordinate amount of time on this, but I will point out some observations you could make potentially by taking a look at these maps, at least observations I've made. For example, in the upper right-hand corner, looking at this map, you get some sense that we've observed quite a number of increasing trends along the shorelines of Farmington Bay, that lower right-hand corner of Great Salt Lake. And then you take a look down at the 2 lower panels, and you can see in the southern end of Farmington Bay, you have quite a few numbers of species and groups that are declining as well down there. So there's some broad brush observations based on these 4 maps about where you might see concentrations of increasing and declining trends at the lake. But we can actually dig into the results for individual survey units, and I'm just going to illustrate two of those really quickly here. One of these that I've chosen to illustrate is Bear River Migratory Bird Refuge, U.S. Fish and Wildlife Service property. The survey unit that corresponds to it is illustrated with a black arrow on the left-hand side, the map there. And for this particular survey unit, we've seen in both fall and spring a mix of species across waterfowl, shorebirds, and waterbirds that have shown increasing trends across that 21-year period. And we didn't find any that were decreasing. One specific species I want to draw attention to is the long-billed curlew. The reason I want to do that is the refuge itself has called this species out as being a focal species in a 2004 habitat management plan. And it's also lumped into a larger group of large-bodied shorebirds for the current draft habitat management plan for the refuge. This is also a species that was a threshold species when it comes to having Bear River Bay itself identified as an important bird area by BirdLife International. So this is a particular species that, because of the numbers that are present in Bear River Bay, contributes to that area being recognized as being really important for birds. The second property I want to just take a moment to highlight is Farmington Bay WMA. And so at this particular property, we saw a mix of both increasing and decreasing trends across the three broad taxonomic groups of waterbirds, waterfowl, and shorebirds. I particularly want to draw attention to the fact that at this particular survey unit, we observed every individual species that shows a declining trend. So all those on the right-hand side there were called out as being, or as having this particular area being important to them. So the WMA itself has identified it as self-identified as a particularly important area for these species that have shown declining trends over this 21-year period. And so, maybe this is something that gets wrapped into management planning at the WMA, and they think about ways that they could potentially stabilize or lead to increasing trends for these species going forward. And similar to the long-billed curlew, I also want to draw attention to the fact that the American habiset and black-necked stilt here were two species whose numbers also contributed to having Farmington Bay recognized as an important bird area by BirdLife International. So that's also an important footnote to consider when we make this observation that they've been declining, at least at this particular survey unit in Farmington Bay. Okay, so I've shown you that you can take a look at these local trends by individual survey unit, that those local trends might be able to inform some management decision or conservation action decisions for those local survey units. But you can also look at these local trend results by species. And I'm just going to show you one example of this. This is the results that we produced for the eared grebe in spring. And we've got two pairs of paired maps and panels, left and right here. The left-hand side shows you the average abundance index for eared grebes. So these values span in the map from a light green to a darker blue, going from less to more abundant for this species. And so taking a look at this map, you get some sense of where the species was most abundant over that 21-year period. And on the right-hand side, what I'm actually showing you are the trends results for each of the individual survey units, going from the red color being a negative trend up to the darker blue color being a positive trend for the species. And if you take a look, you'll see at the lower panel, there are at least 4 survey units that are colored red, where that Bayesian confidence interval does not overlap 0. And so those are actually 4 survey areas, or survey units rather, scattered throughout Great Salt Lake, where there are significant declines for this species over that 21-year period. And so maybe if you're an individual who's particularly interested in eared grebes and eared grebe problem areas at the lake, this could guide you to locations where you might think about conservation or management actions to improve conditions for the grebes in those particular locations. All right, so some take-home messages based on this body of work so far. Across the network of saline lakes in the arid west, we know from previous work that there's been a decline in water resources available to both lake and wetland habitats. And I'm illustrating this broader network of saline lakes on the right-hand side there. Great Salt Lake is the rightmost water body in that image. And then the rest of the image is basically illustrating migratory connections for various water birds, waterfowl, and shorebirds that move across the Great Basin. And as I just said, we know that water resources have been declining at the nodes within this network, at least over the last several decades and much longer, in fact. With that context in mind, that conditions are deteriorating at a regional scale, I would say that this observation that we have stable or positive aggregate trends at Great Salt Lake is a good thing. It definitely reinforces the value of Great Salt Lake as a part of this network and is continuing to support these bird species. However, I will hasten to note that we really aren't able at this point to state why we have stable or positive trends at Great Salt Lake. And from my perspective, I think that's important to continue investigating and to parse out, because the reasons behind these different reasons potentially behind these trends have different implications. And I'm just going to name off a couple of potential explanations. One, as I just said earlier, regional habitat is on the decline. And with that as a regional context, it could mean that the birds have fewer options and they're being forced to Great Salt Lake regardless of whether the habitat conditions for the birds are good, bad, or other at Great Salt Lake. So they're just being forced to Great Salt Lake because of declining regional habitat conditions. On the other hand, and this isn't necessarily mutually exclusive, it could be that habitat at Great Salt Lake is stable or improving, depending on the species or group that you're looking at. And so I think you get some sense that those are very different interpretations of why we have these stable and positive trends. And it's important to continue looking into that and sort of parsing out what's really going on here. I hope that I illustrated, even if quickly, what the potential uses are for the local trends that we showed for individual survey units, helping to identify for those individual survey unit species that might be declining, could lead to prioritization decisions regarding what species or groups might be high priorities. And then for individual species, like the eared grebe map and panels that I showed you earlier, can help you identify for those individual species where you might really have some problem areas around the lake that you would want to prioritize working at for that species. Just a few more slides here. So I want to emphasize that because we're not really able to say why we have these stable or positive trends at Great Salt Lake at the moment, we really can't take them for granted. And of course, securing those trends will require basically the implementation and carrying out an adaptive management approach where we set objectives for populations and habitats, identify and address limiting factors that prevent us from meeting those objectives. And given that we're talking about really a focus on migratory birds with this particular data set and this analysis, I think it makes sense to look at things through a bioenergetics lens and ask when they're moving through and using the lake, are there sufficient food and energy resources for them to survive while they're there and to prepare for the next leg of their migratory journey. And then finally, of course, as an adaptive management approach, continued monitoring, such as what GSLEP is doing, to allow us to assess progress towards objectives and adapt as needed if our conservation and management actions aren't successful in allowing us to meet those objectives. And then just one last pair of slides here. Another body of work that has sort of emerged out of this collaboration between Audubon and GSLEP is really a thought process about how GSLEP might be able to enhance the value of the monitoring program going forward. And one of the suggestions that I think we put on the table is taking a look at the survey units they're currently including as part of this long-term survey effort that they have. If you remember early on, one of the things I said was that they selected survey units that were highly used by the birds and assumed to be of high habitat quality. And there are at least some models of bird settlement and bird habitat selection that would suggest that these are actually the areas where you might detect a population decline last. And birds might actively move into those areas and maintain their numbers over time. So if you want to be able to detect declines early on in that decline process, you might actually want to actively select some areas you think are of lower habitat quality and aren't used as heavily by the birds. And there's another limitation associated with the current survey units in the sense that these survey units don't include all the habitat types we know are potentially important to some of the groups that are being surveyed. So shorebird playa habitat is just one example of a habitat type that's not really heavily represented right now in the current survey effort. So just to reemphasize something I said earlier, the trends I'm reporting here today, especially the aggregate trends, really only pertain to these 24 survey units, and they shouldn't be extrapolated beyond those 24 survey units and used to make broad statements about what's going on with the birds at Great Salt Lake. Some other suggestions quickly: observer training to help improve the ability to differentiate between some of those tough to identify species. So going back to the Western and Clark's grebes that I talked about earlier, maybe through training, we would improve observers' abilities to pick those species out and differentiate between them and avoid the need to lump them into groups during an analysis like this. One other point here, recording additional nuisance variables, what I refer to as nuisance variables. So of course, we all know development is continuing around the lake, and just one example of what I'm referring to as a nuisance variable would be something like ambient noise. So if ambient noise levels increase, you could see that potentially confounding the ability of observers to detect, record birds, and our ability to then have confidence in the trends that we're finding through these analyses. And one other limitation associated with the current monitoring program would be that they don't simultaneously collect habitat data along with the bird counts. And so this is a bit of a hurdle when it comes to answering the questions that I posed earlier about why are we observing these trends across time, because we don't really have a strong ability currently to link the bird counts to habitat features that might be causing those trends. One way around that we're exploring right now is to use other data sets from existing monitoring programs like the USGS flow gauges and thinking about surface water inflows, or using satellite-based imagery to do some interpretation and analysis of what the habitat conditions might have been in the survey units when the surveys were done. So looking at things like percent water cover, bare ground vegetation. And we're currently in the process of analyzing relationships between bird counts and those derived habitat metrics. That work is in the process of being drafted and shared with everybody who's going to be a co-author on that. I will say that I should also note, I didn't have a bullet point here about products or where things are at with the trends analysis that I showed you earlier. We've gone through the process of drafting a manuscript. That manuscript is currently under review at Wetlands Ecology and Management, a peer-reviewed scientific journal, and it's been under review for about 2 months now, so I would suspect that we'll be hearing back anytime now regarding the journal's decision on that manuscript. With that, though, I'll thank you for your attention, acknowledge the following folks who contributed greatly to the monitoring program and our analysis to date, and I'll take any questions anyone might have about this.
Any questions for Brian?
Let's see if we've got questions in the chat, John.
Yeah, I don't think so. I know one of the things you mentioned about training and some of the issues that where we had to lump things in are with respect to aerial surveys. So Clark's grebes, Western grebes, no amount of training is going to help you differentiate between the two of those from the air. It's just a matter of covering certain areas. So obviously, if you're in a truck and you're able to look at Clark's or Western grebe, you can tell. But some of the reasons that we were able or lumped those together were specifically because of they dealt with aerial surveys, and we knew we couldn't parse those out.
Right. Yeah, and there's some species that are just going to be a problem regardless of whether you're in the air or on the ground. Like the sandpipers are a problematic group, I would think.
Yeah. Any other questions? All right, then. Well, I appreciate all of you sticking around for an extended tag meeting and going through your lunch hour. Is there anything that anybody wants to bring up before I throw out some dates for the next meeting?
Hey, John, I just wanted to let everybody know that the Great Salt Lake biology book is out. And I could put a link in the chat box. And anybody, many of you in this room are authors on chapters in that book. So I have a lot of gratitude to all of you, and just want to say thanks for your participation. If you are authors, you do get a 40% discount off buying books. And the money goes to Springer, not to us. So just so you know. Let us know if you're an author and you need that discount code if you don't have it. But I'll put the link so everybody can see it in the chat.
Very good. Anything else?